What's up, my fellow atoms? Today is an absolute worldie of a shapes of molecules question. So let's jump right into the first part. Amides are commonly used in industrial processes as solvents. The smallest amide is methanamide, that's HCONH2, and it's been suggested that methanamide could also act as a solvent. Question is asking to give us the dot and cross diagram for methanamide. So let's start. I always first think about what's going to be the central atom or central atoms. In this case, we're likely to have a carbon as a central atom because it bonds 4 times, and a nitrogen because it forms 3 bonds. So let's start by drawing out a ball and stick diagram or a letter and stick diagram. So with the carbon and the nitrogen in the center. So we know the hydrogen can only bond once and it seems to be bonding to the carbon. So let's put that in. Then we know the oxygen needs to double bond. So it could bond between the two, so a shared bond, one going to the carbon and one going to the nitrogen. But that would mean that these 2 hydrogens have no place to go because they cannot bond to the carbon and they cannot bond to the nitrogen. And amides have a functional group of NH2. So this is likely to come as a group. So we can put our hydrogens on. So now we're kind of just left with the oxygen and completing the number of bonds. We know oxygen double bonds, and we know it can't go on the hydrogen because that would make it have 4 bonds, so it must go on the oxygen, on the carbon, sorry. And so finally, to complete this, both of carbon and nitrogen need 1 more bond. We can just bond them together. And so that's our structure of methanamide. So now we need to draw the dot and cross diagram like they've asked for. And this is quite simple from here because we know the bonds that are in them, and it's just a case of getting your lone pairs correct and getting your bonding pairs correct. So 1 bond between the carbon and the nitrogen. There is a double bond between the carbon and the oxygen. So I'm going to represent the oxygen's electrons as triangles. And there is a bond between the hydrogen and the carbon. So I'm going to represent them as, let's say, stars, because I'm feeling fancy. So we can put the oxygen on here, the hydrogen on here. So now we bonded all of our carbon, we bonded all of our nitrogen. This oxygen needs 8 electrons around it, which means that it will have 2 lone pairs on it. Then this nitrogen will have a bond to the hydrogen, which is like this, and another bond to the other hydrogen, which looks like this. But we've got a problem here, in that nitrogen typically has 5 electrons in its outer shell. However, the nitrogen only has 3. 1, 2, and up here 3. So we need to add a lone pair to the nitrogen to complete the outer shell, and that is our dot and cross diagram solving the first part of the question.
Okay, hello everyone, back to it, straight into it, straight onto question B. So predict and explain the HCN and CNH bond angles. Right, so she has already drawn this incredible diagram that I'm just gonna steal off of. Okay, so straight away we'll get into the H, C and N. So C is our central, so we're trying to find this angle right here. Okay, so what we need to look at is, we need to look at the bonding regions and the lone regions, right? So on this diagram we can see we have a bond pair here, a bond pair here, and a double bond pair here, right? No bond pairs, so this will give us a trigonal planar shape. However, we have a double bond here. As there are more electrons, there will be more repulsion, giving us a slightly tighter angle. So what would be the 120 degree, I believe, would go to about 118 degrees. Okay, so we're going to pop that down. 118. Okay, for the first one, for the HC and N. And then for the C and H, right? So we're looking over here around this central nitrogen atom. Okay, so we have the bond pair here, bond pair here, bond pair here, and now a lone pair. Lone pairs also repel slightly more, so this will give us, as we have 4, we'll have a pyramidal shape. Okay, as we'd have the, I'll try and draw it out. So we'll have 1 here, 1 coming close, 1 going far, and then a lone pair up here. So the lone pair would repel it down and it would be like the pyramid. So that would give us off the top of my head, I believe it's around 108 degree. So we'll pop that down, and we'll furthermore draw the shape over here, as typically we would write this out, explain the shape. So we would have pyramidal here and trigonal planar here. So how the trigonal planar would be, if we were looking at it from a bird's eye view, we'd have central, so say this was our central, we'd have 1, 2, 3, this would be our 118, 118, and as this is repelling slightly more, we would have 121 on each side.
So just a little bit more on this shape. On the trigonal planar shape, you can see there's 3 regions of electron density and 3 bonding pairs. So that means that this shape, you will have to write that there's 3 bonding pairs, no lone pairs, 3 regions of electron density, and so the shape is trigonal planar, written like that. And then over here, because there's 4 regions of electron density, the electron shape is actually tetrahedral. But because the top here is a lone pair, it's going to repel more, and also there's no atom there, meaning that it's trigonal pyramidal, and the bonding angle will decrease by 2.5 because lone pairs repel slightly more than bonding pairs.
So with C and D, B and C answered, the thing that we have left to do is prove whether the molecule is polar or not. Now there are 2 criteria for a molecule to be polar, as you've seen in other videos. There needs to be dipoles, so there needs to be a difference in electronegativity between 2 atoms, and the charges need to be distributed unevenly, or there cannot be a line of symmetry about which the charges are distributed, because this would mean that the dipoles cancel out. So let's go back to our diagram here. So we know this, the C and the H bond is, there's no electronegativity difference, that's the definition. However, between C and O, there is an electronegativity difference, where this is more electronegative than the carbon. And likewise, the nitrogen has that as well. The nitrogen is very electronegative, so it has a dipole on it, creating dipoles on both of these hydrogens as well. So we've proven that it has dipoles. Now we need to see, is the distribution of charge even symmetrical? Well, just by looking at it, we can actually see that it's not. Think about this dipole pulling it in one direction, but this is only pulling it in this direction. So if you were thinking about the dipole as 2 people pulling each other apart, those forces aren't going to cancel each other out. Imagine it's going to move this way. Realistically, dipoles don't do that, but it's analogous to that theory. So there is an uneven distribution of charge, which actually tells us that the molecule is polar.